Have you ever wondered how we can use data to predict what might happen next? It sounds a bit like magic, but it's at the heart of what data science is all about. Today, we're going to go on a little journey, starting with something as simple as a line and ending up with the incredible wisdom of crowds. Let's dive in. To make this real, we're going to focus on one single question the whole way through. Can we use data to predict someone's salary? You know, using things like their age, their education, maybe even if they have health insurance. This isn't just some abstract puzzle. It's a real-world problem that's going to be our guide through all of this. So, you're going to hear me say the word model a lot. But what is a model, really? I absolutely love this quote. Every analytical model is a bridge. Think about that. It's the bridge we build that takes us from a bunch of raw data and all its messy patterns to an actual, useful outcome that helps us make a better decision. It's how we turn info into insight.
All right, so our journey starts with the most basic tool you can imagine, a simple line. But you'll see we can make that line way smarter than it looks, right from the very beginning.
Okay, so the first, most obvious idea is just to draw a straight line that kind of slices through the middle of our data. That's a linear model. But here's the problem. Real-world data is never clean. It's messy, it's noisy, and a simple little line can get really confused and thrown off by all that random static. So how do we help our model focus? Well, we use this really cool technique called regularization. The best way to think about it is like noise-canceling headphones for your model. It helps the algorithm tune out all the junk and the random static so it can actually hear the real signal, the true patterns hiding in the data.
And there are two main ways to do this. On one side, you've got 2, which I call the balancer. It keeps everything in the model, but it kind of shrinks down the influence of each factor so no single one can get too loud. But then you have L1, the minimalist. And this one is way more aggressive. It actually forces the least important factors all the way down to 0, basically kicking them out of the model completely. It's not just noise canceling, it's also a bouncer. So for our wage prediction problem, which one worked better? Turns out the L1 minimalist model was the winner. It gave us an R-squared of 0.339. Now, R-squared is just a fancy way of saying how much of the why behind wage differences our model could actually explain. And in this case, by forcing the model to focus only on the stuff that really mattered, we got a better prediction.
But here's the thing. A line is still just a line. And the world isn't always linear, right? Sometimes a problem is so complex that a straight line just isn't the right tool for the job. So, what do we do then? Well, we start thinking in trees. Instead of trying to fit one single line to everything, what if we just made a series of simple yes or no decisions? This leads us to a totally different way of thinking, a model called a decision tree. Honestly, it's just like a flowchart or one of those old choose-your-own-adventure books, but for data. And you can see how simple and intuitive this is. The model just asks a series of questions. First up, is the person over 24? If yes, they go down one path. If no, they go down another. Next question, do they have health insurance? That splits the groups again. It just keeps doing this, slicing the data into smaller and smaller groups until it lands in a final little bucket with a specific wage prediction. It's a logic you can actually follow.
Now that decision tree is beautifully simple, right? But that simplicity, well, it's also its biggest weakness. What if that one tree with its one set of rules is just wrong? And that question leads us to our next huge leap forward, tapping into the wisdom of crowds.
Yeah, the big danger with a single decision tree is that it can get a little too focused on the specific data we trained it on. It might learn some weird habits or quirks that don't really apply in the real world. I mean, what if its rules are just off? It's kind of like listening to a single expert who, might have a huge blind spot they don't even know about. So, the solution is just brilliant. Instead of building just one tree, what if we build hundreds or even thousands of them? We give each tree a slightly different peek at the data, and we only let them consider a few factors at a time. This is what's called a random forest. And then, at the very end, we let all these hundreds of little expert trees vote on the final answer.
And wow, look at the difference this committee approach makes. That single lonely decision tree, it had an accuracy score of about 0.28. But the random forest, our committee of trees, shot all the way up to over 0.36. It's incredible. By bringing together a whole bunch of different perspectives, we get a much, much stronger and more accurate prediction. It's the wisdom of crowds in action.
And it gets even cooler. Some of these really advanced forest models don't just spit out one single number as the answer. Instead, they can give you a whole range of likely outcomes.
So they won't just tell you the most likely wage, they'll tell you the plausible best and worst case scenarios too. And that gives you a much richer picture of what could actually happen.
So, we've gone from a simple line to a flowchart to an entire forest of decision trees. It's been quite a journey. So, which one is the best? Well, the answer is the most important lesson of all. There is no best model, only the right one for the job.
This little table really sums up the big dilemma. See that random forest? It's our accuracy champion, no question. But it's a black box. We get this amazing answer, but we can't really see how it got there. Then, way at the other end, you have the simple decision tree. It's completely transparent. You can follow every single step of its logic, but it's also the least accurate. And this, right here, is the fundamental trade-off we're always dealing with.
And this is the crucial takeaway from our whole journey. There's this constant tug-of-war between how accurate a model is and how easy it is to understand. Simpler models, super easy to explain. More complex models, usually more accurate. So the real question you have to ask is, what's my goal? Do I need the absolute most precise prediction even if I can't explain it? Or do I need an answer I can actually explain to someone even if it's a little less perfect?
And that brings us to the final question, one I want you to think about. In your world, what would you trust more? A simple answer that you can explain, step by step, or a much more complex answer that's probably more accurate, but you can't really explain how it works? There's no easy answer, and that's really the core challenge of making big decisions with data.